know for your exam. So first of all, there's an in-person review tomorrow after school in A210. If you don't have an exam, just come at 2:30. If you do have an exam, just go up after your exam. But Mrs. Belden's going to be leaving that in A210, so a good place to come get one-on-one help, ask questions. She's going to have stuff planned to go over. Your exam is Wednesday from 7:50 to 9:20. It will depend on what class you're in for what room you go to. My class go to B111. Mrs. Belden's, you guys can see how you're broken up. And extended time, you guys are in B107, and you should have gotten a pass that said that. Also, if you need more help, you guys can check out the Unit 3A live stream. That's still up. It's under Unit 3 on my teacher site. And I also linked last year's Unit 3 live stream, and that's pretty extensive. That's about 80 minutes. So if there's something we don't go through tonight or you just want to see more, please go to those and check them out. Tonight we're going to kind of book it because, again, the 3A stuff is all still up there under Unit 3A. I know there were some people who said, please review 3A because we just did 3B. But all of that is in my last live stream. So we're going to hit the high points. But if you want some more in-depth practice, go back to the Unit 3A review. So these are your topics that you're going to need to know for your test. So for 3A, that was everything that was tested on your last test. For 3B, it's really just optimization and related rates. You are responsible for formulas for area, perimeter, volume of any, or area and perimeter of any 2D shape, including circles, and volume of any prism or cylinder. If you're given a sphere or a cone, we will give you those formulas. But otherwise, this is the culmination of all your math. You got to know them. In this part, the things that I really want to talk about is curve sketching, and especially second derivative test. That was something that my class and Mrs. Belden's class both sort of struggled with on our last test. Mean value theorem was one of the most highly requested topics. And then we're going to hit definitely on optimization and related rates. Other things in here we will hit, but we're not going to spend a ton of time on them. I'm just going to give you guys some reminders. So at any time, send me questions, okay? We're going to start with Lhopitals Rule. So I'm starting with the actual rule here because I want to remember the way this is written. So what Lhopitals Rule actually says is that when the limit of f of x equals 0 and the limit of g of x equals 0, both as x approaches c, that and the limit of f prime over g prime equals L, then the limit of f over g will equal the same thing. So notice the conditions that need to be true here. You must have the limit of f and the limit of g equal to 0 or equal to infinity. It could be either. But you need those limits defined separately. So if you're still somebody who's writing 0 over 0, be very careful with that. That's not the definition of our rule here. So if I'm looking at something like this, and I want to figure out if this is, or if I can evaluate this with Lhopitals Rule. In your head, take a second and plug in 0. So in the numerator, you'd get square root of 1 minus 1, that's 0. In the denominator, you would get 0. But ultimately, when I evaluate this, I don't want to see you writing 0 over 0, right? I would be doing the limit as x approaches 0 of my numerator, which is 0. The limit as x approaches 0 of my denominator, which is 0. And because of that, I can say, therefore, Lhopitals Rule applies. And you guys are in a college course. You can write out the word Lhopitals. You don't need to write LH. And if on the AP exam you wrote LH, they would say, we don't know what you're talking about. So Lhopitals Rule applies. Make sure you write it out. I don't care if you spell it right. So then from there you could say, okay, so then this would be the limit as x approaches 0 of the square root of, the derivative of the top over the derivative of the bottom. Derivative of the bottom is just 1. The derivative of the top is 1 over 2 radical 1 plus x times the derivative of the inside, which is just 1, minus 0. So now when I take this limit, I just get 1 over 2. So just make sure the biggest thing on Lhopitals Rule is that you're showing those two limits separately and then showing that Lhopitals applies there. But generally, you guys were great on that in the last test, so not super worried. All right, continue to send questions at any time because remember, I am doing this and just going through the highlights, so you guys send questions that you have. So next thing we're going to talk about is a linear approximation, or it's sometimes called tangent line approximation. And here's the idea of a tangent line approximation. So let's say I want to know the value of the function at this point, right? I don't know exactly what it is. And maybe I don't even know what the function's equation is. So I can't really figure that out. But I know that the tangent line is this, right? So what we say is that, okay, if I know the tangent at 1 is this, and I want to know the value at 1.1, whatever the tangent line equals at 1.1 should be a pretty good estimate of what the function equals. So what we wind up doing is finding the equation of the tangent line and then plugging in my x value because it should be a good approximation. So if I look at a problem like this, the approximate value of y equals 1 over radical x at x equals 4.1 attained by the line tangent to the graph at x equals 4 is what? The line tangent to the graph at x equals 4 tells me to find the tangent line at 4. So remember, to do that, you need a point and you need a slope, right? So your point, well, I know that x is 4. To get my y value, I'm going to plug into this. So that would be 1/2. So that's my point. And my slope is going to be the derivative. So to find the derivative of that, I'm going to take a second and rewrite that. So y is actually x to the negative 1/2. And take the derivative. So y prime is negative 1/2, x to the negative 3/2. And it might help you here to rewrite this as a radical. So the negative is going to flip it to the denominator. The 3/2, remember, will be the square root and then cubed. Or cube it and then take the square root. And I'm plugging in 4. So this is negative 1 over 2 square root of 4 cubed. Or negative 1 over square root of 4 is 2 cubed is 8, so 16. So this is my slope. So now write that equation. I would have y minus 1/2 equals negative 1 over 16x minus 4. And I want to know what that is when x equals 4.1. So I'm plugging that in for x. So y minus 1/2 equals negative 1 over 16 times 0.1, right? 4.1 minus 4, which is just 1/10. It helps me to write it as a fraction because I see my answers are fractions. So this is going to be y minus 1/2 equals negative 1 over 160. Add 1/2 to that, so y equals negative 1 over 160 plus 1/2 is 80 over 160, sorry. So this is 79 over 160. And that would be my approximation there. So that's your basics with tangent line approximations, right? Find the tangent line and then plug in. And make sure with your tangent line you're using a point and using a slope. Okay? All right. Next thing we're going to talk about is curve sketching. And my biggest emphasis on this, guys, has nothing to do with your actual calculus. It has to do with efficiently using your calculator. Because I saw a lot of people on the last test just not using their calculator efficiently, right? If I gave you a function for f prime and I wanted to know where f prime changed signs, you don't need to go through crazy sign analysis. You can look at the graph and see where it changes signs, right? You can use second calc 0. So all of those things that you know how to do, take advantage of them. Use them, okay? Because what I saw is a lot of people who did their calculus beautifully made a little algebra mistake and wound up losing points. Especially on a problem where it's calculator, they're going to assume that you know how to do it on your calculator and there's not going to be a ton of partial credit built in. So just don't forget that you have the end derivative function on your calculator. You also have the graph. You can solve equations with it. So when you have your calculator, use it. But we're going to go through one of these totally without our calculator, and then we're going to do a couple multiple choice that sort of ask you to apply. So let's say I give you this, f of x equals x cubed minus 3x squared plus 4. And I want you to find all relative max, all relative mins, concave up, concave down, and points of inflection. So we're going to kind of run the gamut once on this, so we make sure that we're up to date on where everything is. So for this, I would have, okay, to find mins and maxes relative, I'm going to use the first derivative test on this one. We're going to use the second derivative test in a second. But let's do a first derivative test. So I'm going to find f prime, which would be 3x squared minus 6x. Right? 3x squared minus 6x. And to find my first derivative, I first need to find the critical values, which remember are anywhere your first derivative either equals 0 or is undefined. This one will never be undefined, so I'm just looking at where it equals 0. So x equals 0 and x equals 2. And then I need to make a sign chart for this. So I'm going to make my sign chart 0, 2. You can go through and test values, but I would look at this and say, this is a positive quadratic. So it is going to be positive, negative, positive, because think about your end behavior, right? It's going up like that. So knowing that, there is a relative maximum, relative max, whenever our slope goes from positive to negative. So this is at x equals 0, and there's a relative min at x equals 2. Now, it does not say find the location of them, right? It says find them. So I need to find the y values here. So for A, the relative max value would be at 4, because plug in 0 to f of x. And for B, plug in 2. So that would be 8 minus 3 times 4, which is 12, plus 4, so that is 0. So remember, location versus actual value. All right, intervals of concavity. Anytime you see concavity, we're talking second derivative. So f double prime is 6x minus 6. That would equal 0. And remember, you should show that you're setting it equal to 0 because I got to know where this 1 came from. It didn't just fall down from the sky. So show that you set it equal to 0 and then solve. So that is my point where I could have a point of inflection. Doesn't mean it is, but we need to check it. So this does change from negative to positive here. And because of that, first of all, this is the point of inflection at x equals 1. And intervals where it's concave up would be when your second derivative is positive, and concave down where your second derivative is negative. So that's sort of a basic overview of all the curve sketching stuff. And I know that's not so difficult, but let's look at a couple multiple choice and make sure we're feeling okay with this. So the graph of a twice differentiable function is shown above. Which of the following is true? And then it's asking you about f, f prime, and f double prime. So let's think. This is a graph of f, right? So I'm looking at this for f of 1. F of 1 is 0. I see that from my graph, right? So now let's think about f prime at 1. F prime is the slope of f. And if I look at that, that is positive. I don't know exactly what it is, but I do know it's positive because that tangent line has a positive slope. Now let's think about our second derivative, f double prime at 1. So f double prime, the second derivative will tell you about the concavity of f. And this is concave down, which tells me that is 0. So if I put these in order, f of 1 should be in the middle. That's greater than f double prime, and that's less than f prime, because one's positive, one negative, is 1, 0. So this is D. Yeah. All right, let's look at another one. At which of the 5 points on the graph is dy dx greater than 0 and d squared y over dx squared greater than 0? So remember, this is just your first derivative. If your first derivative is positive, this means that y, your original function, should be increasing, right? Its slope is positive. For this one, I'm looking at the second derivative. If the second derivative of y is positive, that means y should be concave up. So I'm looking for a point where y is both increasing and concave up. Well, at A, it's decreasing. At B, that looks like a contender, increasing and concave up. At C, it's concave down. At D, it's concave down. At E, it's concave down. So B would be my solution here. All right, next one, second derivative test. This is going to be the last thing for curve sketching. I would say this was probably the most missed question on the last test because you guys are so used to first derivative test, you forget that this is an option. So first derivative test was what we did up here when we said, okay, let me find my critical values. Those are the candidates for my maxes and mins. And then I'm going to look for a sign change. Second derivative test is usually even faster than that. We find the candidates, which are still our critical values, and instead of having to look for a sign change on either side, we're just going to look at the concavity. Because if I know that the first derivative equals 0, then I know that there's a slope of 0 there, which means it's going to flatten. It's going to be a max, it's going to be a min, or it's going to be a point where it just flattens out. So your options where your first derivative is 0 is going to be, it's just flat and there's not actually an extrema there, a minimum or a maximum. So what we look at is what happens to the actual function. If it's concave up, that would mean we have a min. If it's concave down, that would mean we have a max. And if there's no concavity, or if we're not sure, then we need to check another method. So if f double prime is positive at that point where f prime equals 0, there'll be a min. If f double prime is negative, then there'll be a max. And if f double prime is 0, then the test is inconclusive. It doesn't mean that there's not a max or min. It just means the second derivative test didn't work for us there. Okay? So let's look at this one. So f of x equals that. Find all relative extrema using the second derivative test. So let's start by finding our critical values. The same thing we do if we were doing first derivative test. Anytime you're looking for relative extrema, you should be finding critical values. So f of x, before I take a derivative, instead of having to do product rule here, I'm going to make this x to the fourth minus 4x cubed. And f prime then is going to be 4x cubed minus 12x squared. So I can at least, set this equal to 0 now. Take out a 4x squared, so that's x minus 3. So my critical values are at x equals 0 and x equals 3. Now, if I was doing first derivative test, I would make a sign chart. I would look for a change there. We're going to do the second derivative test, which means let's take the second derivative, which would be 12x squared minus 12. Nope, 24x. And we're going to plug in those points. So I'm going to find f double prime at 0 and f double prime at 3. So f double prime at 0 gives me 0. So think about what that means. That means we have a critical point, but there's no concavity there. So this is inconclusive, and we'll talk a little bit more about that one again in a second. Okay? F double prime at 3, so this would be 12 times 9 minus 24 times 3. So this would be 72, and this would be 12 times 9 is 90, 108. And I don't really care what that is, but I do know that that's positive. So here's what this tells me. At this one, my second derivative is positive, which means that this is concave up, so it's going to be a minimum. So there is a relative min at x equals 3 because f prime of 3 is 0, right? It's a critical value, and f double prime of 3 is positive. Now, this one's inconclusive, so the second derivative test failed. So if you still wanted to check that, what you would do is you would go back to the first derivative test. So I would say, okay, let's look at 0, and let's look at the first derivative, which was this, and let's test on either side of 0. So if I plug in -1, I would get -4 minus 12, that's negative. If I plug in +1, I would get 4 minus 12, that's negative. Notice there's no sign change there, right? So no relative extrema at x equals 0. That won't always happen if second derivative test is inconclusive. Sometimes you will get one, but in this case, we had one where second derivative test was conclusive and one where it wasn't, and you still had to use first derivative test. And I know a lot of people will say, okay, why do we need it, right? What's the point? Well, the point is there will be times where all we have is the second derivative. And as you move into Calc 2, the second derivative test will be way easier when you start talking about maxes and mins of three-dimensional spaces, which sounds scary, but it's not that bad. Okay, so let's do our very last thing with actual maxes and mins, and that is the extreme value theorem or the candidate test. So when we did this, at least in my class, we watched Wolf-Flitzer. Remember, in this case, we had an absolute minimum, poor Wolf, terrible, an absolute maximum, and then we had this other candidate who, she was in the game, but she wasn't going to win because it wasn't an absolute min or an absolute max. Notice that I had endpoints on this interval, right? And then you could also have candidates that were outside your interval, Mrs. Dronda sitting at home yelling at the TV. And I might have all the right answers and be a maximum, but it doesn't matter because I'm not in the interval, right? I'm not in the game. So let's take a look at this one. Find the absolute max value. And right away, in my mind, I'm thinking that means y value of this function on the interval from -1 to 2. So the first thing you need to consider is my interval. And my interval has endpoints, and those can be relative extremas. So I'm going to start with those. So if I plug in -1, I would get -2 plus 3 plus 12 plus 1, and that gives me 14. And if I plug in 2, I get 16 plus 12 minus 24 plus 1. So that is 5. Now, we need to see if there's any other possible maxes or mins. And for that, we're going to look for critical points. So f prime is 6x squared plus 6x minus 12. And the the zeros of that would be plus 2x minus 1. So I get x equals negative 2 and x equals positive 1. Now, negative 2 is not on my interval, so I'm going to reject that, right? Don't worry about it. Positive 1 is on my interval, so I'm going to plug that in and evaluate it. So this would be 2 plus 3 minus 12 plus 1. So I can already tell this isn't going to be a maximum, but this would be 6 and then minus 12, which would be negative 6. So my absolute max value here is 14. Remember, for absolutes, test your endpoints and test any critical values on the interval. All right, last thing we're going to look at in this first half is mean value theorem, I think, right? Particle motion, but we're going to spend 30 seconds on that. Okay, so mean value theorem and intermediate value theorem. Ideally, guys, we've got to look for what our response should be. Remember, intermediate value theorem says if f of a is this and f of b is this, and we have a continuous function on the closed interval, we have to hit every value from f of a to f of b. Mean value theorem says that if f is continuous on the closed, differentiable on the open, then we will have a place where the average rate of change equals the instantaneous. And there's more on this in my last live stream. So if you need something more in depth, any of those last 2 live streams I recommended at the beginning would be good for you. But ideally, when we talk about, mean value theorem, we're saying since f is continuous on the closed and differentiable on the open, by MVT there exists a C on AB, between A and B, such that the derivative, this should be at C, equals f of b minus f of a over b minus a. And remember, all that's saying is the slope of your secant line equals the slope of the tangent line at some point. They're parallel, right? So I want to start with this, finding what the error is. So a lot of people on your last test said this, and I took off on everyone's paper. I don't know if Miss Baldwin did, but this is something the AP would take off for. So since f is differentiable on the open interval from a to b, it is continuous on the closed interval from a to b. Take 30 seconds, maybe not even, and think about what's wrong with that. Because there's something that is not right there. Did you think of something? Hopefully. So here's what's wrong. You are telling me that it is differentiable on an interval that does not contain a and b, right? So what you're telling me is that it's differentiable, if that's f of a and f of b, it's differentiable from there to there, which it very well could be. That's great. But then you're saying because of that, that means it's continuous on the closed interval. Now, this is an open interval. It is smaller than the closed interval. You cannot tell me something about the closed interval because you know it on the open interval. So this is something you have to be really careful of. If you had said, since f is differentiable, period, right, it is continuous on the closed, that's fine. But you can't use an open interval to talk about a closed interval because an open interval is a subinterval of your closed interval. So be careful with that. Don't make a statement mathematically that's going to backfire and not be true on you. What I would say is if you're in doubt, just say since f is differentiable, which normally they say in the prompt, then it's continuous on the closed. But be very careful saying this. What I would change this to is just f is differentiable on AB, and then just say and f is continuous on AB, okay? So just be careful with that, right? Be very careful. All right, we're going to look at 1 or 2 of these. So let f be the function f of x equals negative x cubed plus 3x plus 2. What are the values of c that satisfy the mean value theorem? So let's go back to what mean value theorem said. It said there exists a c such that f prime of c equals f of b minus f of a over b minus a. So c is the x value where those slopes are equal. Okay? So first of all, is this satisfying the mean value theorem? Well, it's a polynomial, so it's continuous and it's differentiable. So what the mean value theorem says is that there's going to be a place where f prime of c will equal f of 3 minus f of 0 over 3 minus 0. And what we need to do is figure out where that c is. So let's figure this out. Our derivative is negative 3x squared plus 3, right? And I want to know when that equals f of 3 minus f of 0 over 3 minus 0. So this is 3 minus 0. F of 0 is 2, and f of 3 would be negative 27 plus 9 plus 2. So that is negative 16. Is that right? Negative 27 plus 9 is negative 18 plus 2 is negative. Yeah, okay. So this is really saying, when does negative 3x squared plus 3 equal negative 16 minus 2 is negative 18 divided by 3 is negative 6. That's what it says. So now I just need to solve that. So add 6 to the other side is negative 3x squared plus 9. Factor out of negative 3, so x squared minus 3. And so I get x equals plus or minus radical 3. Now, my only question is, are those both on the interval? So square root of 3 definitely is. It's between 0 and 3. But the negative one is not, so we would reject it. So I would only take C as my answer there. All right, let's look at another one. And these kind of multiple choice tend to trip people up because there's a lot of different things going on here. So f is continuous on the closed interval and differentiable on the open interval. So here's what I already know. IVT applies because it's continuous on the closed. MVT applies because it's differentiable on the open. So it could be either of those, right? EVT also applies because it's continuous on the closed, which means we have a max and we have a min, okay? So which of these could be false? So let's kind of read through these. And sometimes it helps before you do this to actually figure out what MVT would say. Because MVT would say that there exists a point where f of 5 minus f of negative 1 over 5 minus negative 1. This is what MVT would say, right? That point exists. So I'm going to figure out what that is. So MVT would tell me that there's a place where f of 5 is negative 2, f of negative 1 is 4, and this is 6, so equals negative 1. So by MVT, there should be a place where the derivative equals negative 1. So I can already tell you that E should be true. That's MVT. Now, C says there exists a place where the derivative would be 0. MVT didn't prove that, so I'm going to put a star by that one as one that's fishy to me. But let's look at the others. So on this one, there exists a C such that f of C is less than or equal to f of x for every x. What this is saying is that there is a minimum value. Well, if this is continuous on a closed interval, by EVT, there has to be a minimum. So A is true. Now, B says that f of C has to equal 0. Well, we know that f starts at 4 and ends at negative 2. So by IVT, it does have to equal 0, right? There has to be a place where it crosses. And the same argument goes for D. So I know it starts at 4 and ends at negative 2, so it's got to go by 2. That's IVT. So really, C is my answer here. And notice how by figuring out what MVT was going to say first, I already kind of picked that one out as the one in the bunch that was not good. Okay, so we are going to take a look at particle motion and then move on to 3B. And I'm not going to spend a lot of time on particle motion because you guys are killer at this from physics. But here's the one thing I want you to look at. In this problem, the accompanying figure shows the velocity, v equals f of t, of a particle moving on a coordinate line. A says when does the particle move forward and backward? That's fine. B says when is the particle acceleration positive and negative? When does it have the greatest speed? Okay, so here's what I want you to think about. I want you to think about B. If this was the answer I gave, what would be the problem with it? Take 30 seconds and see if you can tell what the problem would be there. And then we are going to talk about that. Okay, so here's my issue. This function is v. In yours, you said the particle's acceleration is positive on 3, 6 because a prime is greater than 0. So a couple issues. Number one, like, we're not looking at A, right? We're looking at V. Number two, you're talking about A prime, which is the derivative of acceleration. So if you were going to mention this, here's what I would say. I know that you want to say because A is greater than 0, because acceleration is positive when A is greater than 0. But they gave us V. They gave us F, right? So if you're going to say something about this, you have to talk about it in terms of V. So what I would say here is V prime is greater than 0, right? V prime is greater than 0. Notice I didn't even say because V is increasing, because I want to talk in terms of calculus here. Now, if at some point you said let A equal V prime equal F prime, then you could start talking about A. But unless you have specifically defined A, to me that's just a variable. I know in physics class we would assume that that means acceleration, but we don't do that in calculus. All right, so that is 3A. There is more on that. There's a whole live stream on that if you want it. We are going to go to 3B, and we are going to kind of hit the high points on this. If you want even more practice beyond what we're going to do right now, I would really encourage you to go to last year's live stream and look at even more of it, okay? So here's the thing. When you optimize, and by the way, this is a pretty small topic on the AP, so if this is something you're getting stuck on, I would say between this and related rates is really the one on the AP that's going to be huge. So when you optimize, here's what you need to know. You need to have something that you're optimizing, which just means find a max or a min, and you need to have constraints, which are limiting factors. So we're going to start real simple here. So find two positive numbers such that their product is 192, and the sum of the first three plus the sum of the second three is at a minimum. Okay? So let's start with what do we know and what are we trying to optimize? So product is 192. That is just a constraint. Okay? There's nothing that I'm optimizing there. It's just a constraint. The sum of the first, so that would be like x, and plus 3 times the second is a minimum. So here's what I'm going to say. The formula for this sum is the first plus 3 times the second. And this is what I'm trying to minimize. So when I do this, that's what I'm going to take the derivative of. Whatever one you're trying to minimize, that's the one you're taking the derivative of. So when I do this, I'm going to isolate a variable and go from there. So I'm going to start by solving this for y, let's say. So y equals 192 over x. And I'm going to get this all in terms of one variable. So x plus 3 times 192 over x. Now, let's do some calculus to this, right? So that's really what you're looking for. Find the dimensions of the circle and square. So that's your radius. To get your square dimensions, you could plug that back in to your side length formula. Okay, let's look at one more, and then we'll talk some related rates. So a rectangle is bounded by the x-axis and the y-axis, and the graph of y equals 3/4 x, 6 minus 3/4 x. What length and width should the rectangle have so that its area is at a maximum? So let's take a look at this. So to find this area, I would have to do length times width, right? So area is the thing I'm trying to maximize. And so that's going to be, think about it as like length times width, right? Now, what are my constraints? Well, my point has to be on that line. So I know that that's a constraint. So what I would say is, let's sort of label that point. So this would be x, and then y, which I know is just x, and then 6 minus 3/4 x. So, knowing this, that's my x-coordinate. This is my y-coordinate. My area is just x times 6 minus 3/4 x. So that's what I'm trying to optimize here. So I'm going to distribute that x out. So 6x minus 3/4 x squared. Excuse me. And now I can optimize that. So a prime is 6 minus 6/4 x. Set that equal to 0. And subtract 6 over and then multiply by 2/3. So x will equal 4. And it says what the length and width should this have. So I know that the x is 4. So my y is going to be 6 minus 3/4 times 4. So that should be 3. So this would be 3 units by 4 units. Okay, send me optimization questions. I know you guys are still out there and no one sent any questions. If you want more optimization questions or practice, you can go back to my live stream from last year, but I do want to leave enough time for related rates. So for the last 15 minutes, we are going to go to those. Okay, so continue to send questions if you have them. The basic idea with related rates is you have a bunch of rates and they are related to each other somehow. So the biggest part is we need to find an equation that will relate whatever my quantities are to each other. Okay, so let's say that I'm looking at this first one, and this is as basic as they get. The radius of a circle is changing at 1 over pi inches per second. So I know that dr dt is 1 over pi inches per second. And it says that that's a positive rate, so this is growing, right? At what rate in square inches, that's giving away what I'm finding, per second is the circle's area changing. So I want dA dt. Now it says when r is 5. R is not always 5. I'm not going to plug that in until my very last step. So I need some kind of a formula that relates the radius of a circle to the area of a circle. And I'm sure you guys can guess. We would use area is pi r squared here. So I'm going to do the derivative of both sides with respect to time. So dA dt equals 2 pi r dr dt. And now you're just plugging in. So they tell you that dr dt is 1 over pi. So 2 pi, they tell you r is 5 at that instant. The pi's cancel, and that is just 10 inches squared per second. So again, that's about as easy as they come, but let's get a little bit more interesting here. All right, so let's look at this cube one. So the volume of a cube is increasing at a rate of 12 inches cubed per minute. So this is dV dt, and it's positive. And I know that that's volume because A, it says volume, and B, it's in inches cubed. How fast is the surface area? I'm going to call that ds dt, increasing when the length of the edge is 20. So let's kind of look at these formulas. The volume of a cube is side cubed, side times side times side. The surface area of a cube is 6 times side squared. So notice what these have in common. They have in common that they both depend on s. And I should pick another variable for that. So let's call that x because I used s for surface area. So they both depend on that x value, right? So I know dV dt. From that, I can get dx dt. And once I know that, I can definitely get ds dt. So this is when, look at how these are connected. They depend on the same variable. So let's start with this one. So dV dt here would be 3x squared dx dt. And dV dt they told me was 12. And I want to know at the instant when the side length is 20. So 3 times 20 squared dx dt. Okay, so this would be 12 over 3 times 400, which is 1200 dx dt. So that is my value for dx dt. Now, let's find the rate that my surface area is changing. So this is ds dt equals 12x dx dt. So let's see what that gives us. So I have 12. They told me x was 20. And before I got dx dt was 1 over 100, right? So let's simplify that. So 20 goes into 100 5 times. And so this should be 12 over 5. And that is answer choice D. So if you get one where it's not so direct, typically they're going to depend on the same variable. And you could solve for the rate one is changing to get the rate the other is changing. All right, we're going to do about 2 more questions. And then if you guys don't have questions, I'm going to be out of here. So let's look at this one. The radius of a circle is increasing at a constant rate of 0.1 centimeters per second. So dr dt equals 0.1. And it says decreasing, so that should be negative, right? Okay. In terms of the circumference, and I'm going to remind myself that c is 2 pi r, right? What is the rate of change of the area of the circle in square centimeters per second? So I want to know dA dt. Okay, so let's start by just thinking about A. This is a circle, so area is pi r squared. So dA dt, because that's what I'm trying to find, so let's kind of start with that, would be 2 pi r times dr dt. Now think about what I know. dr dt is negative 0.1 times 2 pi r. And it's said in terms of circumference. C is 2 pi r, so that is 2 pi r. So here's what I actually know. dA dt is C times negative 0.1. And that, my friends, is letter B. So sometimes they're going to ask you to express everything in terms of variables. It happens. Don't let it freak you out. All right, this is my last question that I have planned. So we're going to do this one. And then from there, you guys can ask me questions or you can head off. I know some of you guys have other tests tomorrow. So a funnel is in the shape of an inverted cone. So inverted, think upside down. There's my funnel. Has a diameter across the top of 20. Normally, I like to just mark the radius then because typically we're going to use radius. And a height of 30. Liquid is flowing out of the funnel at a rate of 12 centimeters cubed per second. Because I see those units, centimeters cubed, I know that that is dV dt. And volume is decreasing, so that's negative 12. At what rate is the height decreasing? So dH dt. At the instant when h is 20. So notice, I'm given h, I'm asked about h, and there's no radius mentioned in this whole thing, right? So what I would say is this is a prime candidate for getting rid of radius. So I know that volume of a cone, is 1/3 pi r squared h. So I'm going to start by thinking about what is this in terms of just height. So remember that when you build a cone like this, you really wind up with a pair of similar triangles. That wherever your water level is, your radius and height will be in the same ratio. So, okay, the ratio of radius to height is 10 to 30. So if I solve this for r is 1/3 h. So I'm going to plug that into my equation. So volume is 1/3 pi times 1/3 h squared h, which would give me volume is 1/3 pi times 1/9 h cubed, or 1/27 pi h cubed. So now we want to know dH dt. We have v and dV dt. So dV dt, take the derivative of both sides, is 1/27 pi 3h squared dH dt. We can reduce this a little. 3 goes into 27 9 times. So what I know here is negative 12 equals pi over 9 times, they told me that h is 20, dH dt. And then I can divide this. So this is negative 12 equals 400 pi over 9 dH dt. Multiply by the reciprocal, so I would get negative 108 over 400 pi equals dH dt. Now, let's think about our units for that. Height is measured in centimeters, so that would be centimeters per second. And it says at what rate is the height decreasing? So you could say here it's decreasing at 108 over 400 pi because the decreasing part takes care of your negative. But if you left it as dH dt equals negative, that's fine too. All right, so guys, this was really a crash course through the whole 2 units, or, 2 parts of the unit. If you have questions, send them to me. I'm going to be around for about 2 or 3 more minutes. And otherwise, I would really urge you guys to go back and look at those other live streams if you still have questions. Send me messages. If you're going to be at school tomorrow, feel free to shoot me a message and see if I'm free. But I might not be. Okay, question. How would you do a problem like the last question but with a cylinder? I understand to relate height to radius, but by setting up a ratio with triangles. How would you relate them with a cylinder? Okay, this is a really good question. So what if we'd had the same kind of question but with a cylinder? So think about this. The key and the reason that we had to come up with that ratio here on a cone was because the radius and the height are both changing. Here's the thing about a cylinder. On a cylinder, your radius is consistent throughout, right? So if you were doing volume of a cylinder, volume is pi r squared h. You can, if you know the radius, let's say they told you here that the radius was always 5, or the radius was 5. Before you even take a derivative, you can plug that in because that's not changing, right? So if you know that the radius isn't changing, you can plug it in before you take a derivative. So 25 pi h. And now that's just in terms of one variable. Now the other thing you could do is do product rule. So 2 pi r dr dt times h plus pi r squared dh dt. But when you do product rule, your radius isn't changing, right? So this whole term would just go to 0. And so because of that, you would have, and this would be dv dt, not just v, you would have a whole term there that just cancels out. So when you're talking about a cylinder, if you know the radius, plug it in at the start. If you don't know the radius, you can just do product rule and then go from there. I guess you'd still need to know the radius though, because that depends on it. All right, what else? What else? Final countdown, guys.